Good afternoon, class, or whenever it is that you're watching this video. I'm going to be talking to you about each slide. This chapter, we will be covering all of chapter 2 this week. I will be reviewing it a little bit at the beginning of next week. But in chapter 2, the big deal here is limits and derivatives. We'll be talking about an introduction to limits, limits at infinity, the basic idea of what a derivative is, basic differentiation properties, differentials, and then I'm going to spend a little bit of time on marginal analysis and business economics. These videos will be available with your PowerPoint for each lesson. Unfortunately, every section is just a section of the book, and so it might take a little bit of time to get through this, but I think this will be a little bit more helpful than just putting the PowerPoint on Moodle. So last week, in week 1, it was a very long class. We talked about functions and graphs, and we reviewed linear functions, which is what we see here on this slide. We covered quadratic functions, cubic functions, absolute functions, square functions. I did not cover a great deal of the applications for these functions because we're going to be seeing quite a bit of it throughout the rest of this quarter. I just really wanted to talk about the basic properties of the linear functions, odd and even functions, polynomials, and that sort of thing. And so you can see here that there is a linear function. A graph of a function is a graph of the set of all ordered pairs that satisfy the function. And so here you see f of x equals 2x minus 1. And remember, typically we have probably seen in the past y equals 2x minus 1. But remember, we're replacing the y with this function of x here. And so we're going to look at this linear function to talk about limits. It's the easiest sort of function that we can look at. And we can see here that in this red, it's highlighted, the notation is in red, but we're approaching what's 2. Okay, and you can see that we have 1.5 on the left, 1.9, 1.99, 1.999. We're looking at where x equals 2, what's happening near x equals 2. And then you can see to the right of it, you have 2.001, 2.01, all the way up here to 2.5. So we know what's happening right before 2 and right after 2, but what is the function doing as x approaches 2? And you can see when x is 1.5, f of x is 2, and as we move here towards x equals 2, you can see that the f of x approaches 2.98, and then onto the right of it, you have at x equals 2.5, your function is f of x is equal to 4, and as we approach x equals 2, you can see that your f of x is 3.002. So what is happening as x approaches 2, f of x approaches 3? Now, this seems really obvious, and why am I even spending the time talking about this is because this is the easiest way to look at what is a function doing near this instantaneous point of time. In this case, it's x equals 2. As we move along, when we talk about limits, you can see here this is the limit as x approaches 2. That is how you read that particular notation for the function 2x minus 1 equals 3. Sorry, the limit as x approaches 2 of 2x minus 1, that limit is 3. Okay, that is the limit notation. That is how we write it. So the definition of a limit is right here. This guy that I've just boxed up. The limit as x approaches c, which is a constant. This guy right here is a constant. Here is our function. And here is our limit. If the functional value of f of x is close to apologize there. If the functional value of f of x is close to a single real number L, whenever x is close to but not equal to c, which is our constant. Let's keep moving along. So we have what's called one-sided limits. What is happening on the left-hand side of the limit, which is here, and this is what is happening from the negative side of our constant, and we'll call that k, or the limit from the left, and what is happening from the positive side of the limit. So again, we are just using this linear line to talk about the principles and the observations of a limit. And we're going to get to the meat of what we're doing in just a minute. But in order for a limit to exist, the limit from the left and the limit from the right must exist, and they must be equal. So it's important to understand these definitions. They're going to help us in the long run. So again, notice we're still looking, oh, it looks like we're looking at another function, but we have the limit from the negative side of as x approaches 2, and the limit from the positive side as x approaches 2 here with this absolute value function on the left-hand side. And you can see that as the limit approaches, as x approaches 2, the limit from the negative side is 2, and as the limit from the positive side, as x approaches 2, the limit is 5. Since these two limits are not the same, the limit does not exist. However, in our previous problem, this looks like just a different set of limits. I'm sorry, I thought it was talking about the previous equation. You can see here as the limit on the right-hand side, as the limit as x approaches 0 from the negative side, the limit is 2, and as x approaches 0 from the positive side, the limit is 2. And because the limit on the left and the right-hand side both exist and are equal, the limit exists at 0 and is 2. The limit as x approaches 0 is 2. All right, so some limit properties. The limit of a constant is constant. The limit of x as x approaches c is c. The limit of the sum of the functions is equal to the sum of the limits. And the limit of the differences of the functions is equal to the difference of the limits. So again, just some properties. We'll get into some more work in a minute. Some more properties. The limit of a constant times a function is equal to the constant times a function. And then I'm just going to let you guys read through these. We're going to do some problems that deal with these properties. So you have to remember there's a limit product, limit of the product, limit of the quotient, and limit of the root of a function. All right, so let's do some actual problems here. And so here you can see the limit at this first problem right here, the limit as x approaches 2 for x squared minus 3x. Notice how we broke it up. We said the limit as x approaches 2 for x squared, and minus the limit as x approaches 2 for 3x. Well, as x approaches 2, the limit of x squared is 4. You can see that right here. This is this answer. And the limit as x approaches 2 for 3x, if you just plug in that 2 for the x, is 6. So in case you're wondering, right, so the limit of x approaches 2 for x squared would be 2 squared, right? And the limit as x approaches 2 for 3 times 2. And so that's how we get those numbers. And so 4 minus 6 is negative 2. So that would be the limit of this function right here. You use your properties of limits, and then you're able to solve. So not too hard, right? But these are important things that you need to know how to do. Let's take a look at this rational function. So again, this first one, this is a polynomial. I'm going to make sure that we label all of these types of functions. This is a rational function. Okay, and so we're going to look at this rational function as x approaches 4. We're going to use the property of limit of a quotient. And so we're going to separate this. We're going to take the limit of the numerator, and then we're going to take the limit of the denominator. So the limit as x approaches 4 for 2x is 8, right? So 2 times 4 gives us 8. And the limit as x approaches 4 for 3x plus 1. So this is 3 times 4 plus 1, and that is 13. And so the limit of this rational function is 8/13. And so again, you know, you're just using those properties. It's not too hard, not to understand. All right, so we do have cases where there is no limit, or the limit is what's called indeterminate. And okay, all right, so indeterminate forms. So there are restrictions on some of the properties of a limit. For example, looks like we're doing the quotient of a limit, right, as x approaches c. What if the denominator is 0? Then that limit is indeterminate, and that's all that's important here. All right, so let's take a look at an example here. Here, if you look at this, there is some techniques that can be useful for indeterminate forms. If you look at this original limit here, as x approaches 2, the limit of this is indeterminate. However, if you notice, this is a difference of 2 squares, and so we know that x squared minus 4 is equal to x plus 2 times x minus 2. And so here you see x minus 2 on top and x minus 2 on the bottom, and you're able to cancel those out. And now you're left with just the limit of x plus 2 as x approaches 2. And that is a very simple problem to solve. And that limit is just as x approaches 2 is 4. So algebraic simplification. You are going to do this a lot in every problem that we do and in the future. If you are having some trouble with this, then I really suggest you do some algebra review or practice, kind of doing this back and forth, where you're doing difference of squares and different things that you can do, algebraic manipulation of polynomial functions. All right, so let's keep going. So here is this problem. The limit as h approaches 0, and there is this question here. F of a plus h, which is this guy right here, minus f of a all over h. Now, the reason why I'm really taking my time with this is because this is the definition of a derivative, which we'll be seeing the rest of this chapter. And so we are going to take this function here, f of x is equal to 3x minus 1. And the other reason I'm going to really take my time with this is you will have a problem like this on your midterm on the short answer portion. I will give you a function, and then you need to find the limit of this guy right here that's in the box and has a little x in it. So let's take a look at what our point does. Here you see the solution, and so let's walk through this. Here they find first f of a plus h. They do this first. So notice they're doing it all in parts to give you a little bit of a break. And then they find f of a right here. And so all they're doing is they're taking our original function, 3x minus 1, and they are plugging in what's inside that function. So in this function, f of a plus h, they plug in a plus h in place of x. And so, so it's 3 parentheses a plus h, close parentheses, minus 1. And so you simplify that out, and you're left with 3a plus 3h minus 1. Then here on the bottom, f of a, so instead of the x, they just put an a. So it's 3a minus 1. Now notice here, they're kind of doing the work in parts. They're saying f of a plus h minus f of a is equal to 3h. And let me show you why. If you write it all out, 3a plus 3h minus 1 minus 3a minus 1. All right, and so here we have, we're going to distribute this negative all the way across, and so now you're left with 3a plus 3h minus 1 minus 3a plus 1. And so now we're going to cancel some things out. I'm sorry, my handwriting is a little bit bad. It's the only way I can get the video and while I'm writing, because it's propped up here on the stand. And so 3a minus 3a is able to cancel, and then this minus 1 plus 1 is able to cancel, and we are only left with 3h. And so here we have our original function down here, the limit as h approaches 0. And so if you notice, if we were just to write this out, then h, as it approaches 0, this would make this function or this limit indeterminate. So again, we're doing a lot of algebraic manipulation to find out the limit of an indeterminate form. So that's why I'm sort of taking my time here. So here we have the limit of 3h over h, and those h's cancel out. So the limit of 3x minus 1 using our original function here up top is 3. Why is this important? You are going to see that there's some interesting information here in this